Thank you. Hi, my name is Michael. I'm from UC Berkeley. And I'm going to be presenting Wave, which is a decentralized authorization framework with transitive delegation. So authorization is a very common problem that we all face. So it's kind of useful to ground it in an example that brings out some of the nuances. So throughout this talk, I'm going to be using an example from IoT and cyber-physical systems, because it brings out some of the more interesting parts. So the running example, let's say we have a building owner, and they own multiple buildings. And they're now going to rent a floor of one of these buildings to a company. So they obviously need to grant the CEO of this company access to the cyber-physical assets in the floor that they're renting, so they can control the lighting and access the doors and control the HVAC and so on. But that company also naturally has employees within it. And it's not going to be the CEO who's managing all of these assets in the building. It's going to be delegated to employees. So there's going to be some permission that needs to be shared from the CEO with the employees so that the person who's responsible for controlling the HVAC can do their job. Now, if this were done in the traditional approach, the way that we're all sort of very familiar with, there would be some central authorization server, maybe Active Directory or LDAP or something like that. And all of this authorization policy would be captured on that server. The problem with this approach is that this is a central point of attack. We have a system here where there are multiple buildings, multiple tenants within these buildings, and if this one server gets compromised, all of those tenants get compromised, all of the devices within the buildings get compromised because the attacker can manipulate authorization policy. Additionally, we can't even trust the operator of the server. So on the left-hand side here, the building owner has granted permission to the CEO, but there's likely other similar grants to other tenants in other buildings that they own. And that sort of relationship there is private between the building owner and the CEO. Within the company, there are permission grants to the various different employees, and these permission grants likely represent some organizational hierarchy. So that sort of information is private and it should exist only within the company. If the building owner runs the authorization server, they have visibility into the permission grants that occur within the company. They can see the private permission data within the company that they shouldn't be able to see. And likewise, if the CEO or the company runs a server, they can see permission grants that the building owner is doing to other tenants that they shouldn't be able to see. In addition, in the traditional approach, sometimes delegation is simply unsupported. And you may be familiar with things like LifeX or Netflix, where you simply can't delegate permission to someone. You have to share your username and password, share your whole account. And even when delegation is supported, it's often not transitive. So when the authorization policy is captured in the central server, it's manifest as a set of entries in a central ACL. So if the building owner were to revoke the permission that the CEO would have, that would remove one entry from the ACL, but all of the delegations within the company would continue to be valid. So this is very common, for example, in Google Docs. If you share a document with someone and they share it with someone else, you can revoke the initial person's access, but everyone they shared with retains access to the document. Ideally, what we would want is that when that initial revocation happened, everyone within the company was also revoked. So basically, this comes down to the fact that existing work sort of lacks a bunch of important features that are necessary when you look at more complex authorization cases. So one of the big ones is that a lot of authorization systems have a central authority, whether or not that's a central place permissions are stored or only a central authority that can verify permissions. Additionally, a lot of work out there doesn't have an opinion on how people discover their permissions, which leads to out-of-band mechanisms that may apply additional constraints, like participants having to be online. And most existing work doesn't protect the permissions. They're not encrypted in storage. They're not sort of protected while they're busy being shared between people. So the operators of the infrastructure have a lot of visibility into the permissions. So Wave is designed to provide these missing characteristics. It's a cryptographically enforced decentralized authorization system. And it can be used in place of most mainstream authorization systems. Anyone can delegate permissions or revoke permissions that they have delegated. Anyone can discover permissions that they've been granted and form a proof of authorization. And anyone, including IoT devices, can verify these proofs of authorization. And Wave achieves this using 3 techniques, which I will go through. The first being graph-based authorization, then an encryption mechanism, and a storage mechanism. So graph-based authorization is not a new technique. This was popularized by Sudsy Spooky in 1996. The general idea here is that you represent permissions as a graph rather than an ACL table. So the pictures that I gave earlier, which represent delegation actions between people, now actually represent the real data structure that is used to store the permissions. And this very naturally represents transitive delegation. So in this model, the participants in the system are entities. They're collections of cryptographic keys. And these can be devices, services, or people. And the grants of permissions between them are attestations. These are signed certificates that are created by the entities to represent a grant of permissions. Attestations grant permissions on a resource. And this resource looks like a URI. This may correspond to a device control point, or it may be an API or something like that. These resources are located within a namespace which identifies the entity that created them. That entity, being the creator of this resource, is the authority entity for that resource from which permissions flow. A proof of permissions in the graph-based authorization model is a path through the graph from a namespace authority to some entity that's wanting to prove that they have permissions. So you would assemble two of these attestations together and concatenate them, and that would be a proof that allows you to show that you have permissions on something. And the proof grants the intersection of the permissions of each of its constituent attestations. It's verifiable by anyone, at least in our work, not in Sudsy Spooky. And it's attached to messages and all sorts of interactions to prove that they're authorized. These attestations and entities form a single global graph of authorization. Even though this is a single global graph, there are obviously multiple namespace authorities within the graph. And different entities will only be able to see portions of this global graph through a mechanism that I'll talk about next. The graph is publicly accessible. And so that obviously leads to the question of, well, how do we hide portions of the graph if this is going to be publicly accessible? The answer is a new technique called reverse discoverable encryption. And to set this up, let's take the example that we started with earlier, and let's simplify it a little bit. Let's say the building owner has granted permissions on floor 3 and floor 4 to the CEO. And that CEO now needs to grant permissions on floor 3 to the manager who's going to be in charge of floor 3. Let's also say that the building owner has contracted a separate company in janitorial services, and they need to give them access to floor 3 so they can get through the doors at night to do their job. Now let's say the floor 3 manager is installing a new IoT control service, an HVAC controller in the building. And so he gives it access to some resources on floor 3. And let's look at this from the perspective of the HVAC controller that is now wanting to do the first step, which is discovering the permissions that it has. So if we look at this sort of subset of the global authorization graph from the perspective of the HVAC controller, we see that there's really sort of 3 categories of attestations. The first category are those that lie on a path from the authority to the HVAC controller, and all of the permissions granted by those attestations intersect. So these are the useful attestations. The HVAC controller could take these together, concatenate them, and form a proof that it is authorized to access that resource. There are also attestations that do lie on a path to the controller, but they don't have intersecting permissions, so they couldn't be used in a proof. This one grants on floor 3, the subsequent one's on, first one on floor 4, the subsequent on floor 3, so it's not useful to the HVAC controller. And there are also some attestations that don't lie on a path to the HVAC controller at all. So it's not really relevant what permissions are granted on those edges because it never leads back to the HVAC controller. So the general technique for reverse discoverable encryption is obviously to encrypt attestations. But when you do so, you include in that attestation a secret that allows you to decrypt upstream attestations that have intersecting permissions. And that's basically the first category, those that are useful in a proof that lie on a path and have intersecting permissions. So the HVAC controller would be able to decrypt this first attestation because it's encrypted under a key that it has. And when it does so, it learns some kind of secret that allows it to decrypt this next attestation upstream. And when it does that, it learns a new secret that allows it to decrypt the next attestation upstream that has an intersecting permission. So importantly, it was unable to decrypt these other 2 attestations in red because they didn't have intersecting permissions or they didn't lie on a path. Of course, the challenge here is that the encryption mechanism and the secret that's passed around must somehow capture the permissions in order to be able to enable this. So the mechanism we use is to use wildcard identity-based encryption, which is similar to normal identity-based encryption, except you can have wildcards in the key, so one key can match multiple IDs. But importantly, in our application, there is no private key generator. Every entity in the system has their own YBE system, and the system is used just for RDE, for reverse discoverable encryption, nothing else. So when you create an attestation, when you're granting permissions, you form an ID that is some function of the permissions that is being granted. You then generate the private key corresponding to that ID using your own master YBE key, and you include that private key in the attestation. You then encrypt the whole attestation, including the key that you just included, using the same ID, but using the recipient's YBE public parameters. So it's a little bit simplified. You can see the paper for more details. And what this leads to is a graph that looks a little bit like this, where each attestation contains a key that corresponds to upstream attestations. So the HVAC controller starts off with the orange key because it's its own key. It can generate that quite trivially. So it's able to decrypt this first attestation that was encrypted with the orange lock. When it does so, it learns this light blue key, which is sort of tied to the permissions that are being granted, but comes from Floor 3 Manager, which then allows it to decrypt the next upstream attestation that is also tied to Floor 3 permissions, but comes from the CEO system. Using that, it can then decrypt the next upstream attestation, which is also tied to the same permissions. And it's not really important that this contains a secret key because no one grants permissions to the authority. The authority already has permissions. So importantly, we were unable to decrypt this attestation here, granting permissions on Floor 4, because it's the wrong resource. So because we're using an encryption scheme that is sort of parameterized by the permissions that are being granted, we can ensure that only the keys that we discover are only able to decrypt sort of intersecting permissions. So this remains undecryptable. Also, this one, despite being on a permission that actually is the same as several of the keys that the HVAC controller has discovered, it remains undecryptable because there is no key from janitorial services that is granted to the HVAC controller. There's no path between janitorial services and the HVAC controller. So in summary, reverse discoverable encryption allows us to decrypt these attestations that are useful to us, that we could use in a proof. But it doesn't require any out-of-band communication. There's no sort of key setup phase where we have to communicate. It works when these attestations are granted in any chronological order. And we also, in the paper, show how you can support expiry of attestations using this scheme. Now, the next problem is we have this global graph, and we've encrypted it so that only portions of the graph are visible to entities. They can only see the portions of the graph that are useful to them. But we still need a place to store these encrypted attestations. A blockchain very nearly works. Our initial work did use a blockchain, and we published some stuff on that. It has cryptographically proven integrity. You can store the whole global graph there. People can't tamper with the graph or remove pieces of it. And blockchains don't really have any central authorities. But it doesn't scale particularly well. If you're trying to build an authorization system that sort of has this single graph and multiple parties are interacting with it, it needs to be able to scale to at least the load that current authorization systems are able to handle. And blockchains don't really go past a few tens of transactions per second, especially if the transactions are large. They're not financial transactions, but they're storing objects at maybe 100 kilobytes. So we developed this unequivocal log-derived map, which is designed to provide similar guarantees to a blockchain when you're only storing objects. So it can't do smart contract execution, and it doesn't do financial transactions. But if you're only storing objects, it can get you similar guarantees to a blockchain. It's a horizontally scalable public ledger with cryptographic integrity proofs. And it's similar to something like certificate transparency or key transparency that you may be familiar with, except that it supports a proof of non-existence, which allows for revocation. It also has very efficient auditing. Clients only rarely communicate with auditors, and the auditing load in total scales with the number of additions to storage, not the size of the storage, as you may find in key transparency. And I'll only be able to give a very high-level overview here. You can go and look in the paper for more information. So you have some storage servers, and you have clients interacting with them to discover the portions of the graph that they need to form proofs. There are also some auditors which speak to the servers and are going to be doing something in order to check that those servers are intact and are maintaining integrity. Clients and auditors speak to sort of random subsets of the total set of storage servers that exist. And the storage servers themselves are constructed using 3 Merkle trees. The first tree is an operation log. This stores things like add an attestation, add an entity, or add a revocation. And a Merkle tree log can prove that it is append-only, and it can prove that values exist within it. This gets then turned into a sparse Merkle tree map. And Merkle tree maps can prove that values do not exist within them, and also that values exist within them. Of course, because it's a Merkle tree, it has a root hash, and we take this root hash of the map and we insert it into a third Merkle tree log. So every version of the map that was used to satisfy queries is captured in this log. And this final log, as normal, can prove that it is append-only and values exist within it. The auditors connect to the storage servers and replay the operation log to construct a replica map and a corresponding replica map root log. And they then communicate with the clients to share the root of the map root log. So the clients will send this to the auditors, and the auditors will compare that with what they have reconstructed. And this does 2 things. The first thing is it ensures the object map is properly derived from the operation log. So we know that the operation log is now both append-only and it hasn't had anything removed on it. And we ensure that every client is seeing the same data structure. So there's a family of attacks where servers might give internally consistent views, but different to different clients. We prevent that class of attacks by talking with the auditors periodically. And it doesn't need to be often. It can be daily or weekly. So in summary, the unequivocal log-derived map stores encrypted attestations and entity objects and revocations, and it uses cryptographic proofs of integrity, which force the server operators to be honest or be detected as dishonest, much the same model as certificate transparency. Our auditing, however, only requires very infrequent communication between the clients and the auditors. Wave is a fully implemented system. It's written in Go. There's some crypto that's in C++. We've used various versions of it over the course of 3 years, securing over 200 devices and their associated services in 20 buildings across multiple organizations and multiple namespaces. So we've had a lot of experience with that and the challenges that arise when trying to secure that kind of workload. And it's pretty fast. The graph changing operations, where you sort of grant permissions or change the graph, are very fast by UI standards. Granting permissions takes 45 milliseconds, which is about the length of a perceivable mouse click for a user. And then the hot path operations, like proof building and verifications, are very fast. In our experience, we find that most proofs are less than 5 attestations long. And we find that proof building is less than 15 milliseconds, and verifying that proof takes less than 8 milliseconds. So it's very compatible with existing systems. So in conclusion, Wave is a decentralized authorization system that offers transitive delegation, stores the graph in global storage, it encrypts these attestations, hiding the graph, and it can be used in place of most traditional authorization systems. Thank you.
Thank you. Question?
Well, actually, thank you. We've been looking for this for a long time as the original author of Radius, and I was involved in Spooky. And have you taken a look at how this could be available to improve DNSSEC? All of these, an application. Could be widespread use.
Yeah. Thank you. Yeah, we do see that there are sort of many use cases that you could drop this into, many places where people have stuck a traditional authorization server that you can drop this into, and you gain a bunch of useful features from it. Yeah.
But you haven't actually looked at expanding your field yet.
No, so we've actually used this in a bunch of different places. I used the IoT example running through because it's quite challenging you cross administrative domains. But we've used this to secure sort of gRPC APIs on web services, and we've used this in many places that that would do traditionally.
Does it handle loops well? Like if the HVAC also needed to be responsible to the...
Yeah, the loops are fine. The graph doesn't actually have to be a DAG. You can have loops in it. They end up being not traversed when you're doing discovery, so it doesn't cause any problems. Yeah.
OK, thank you. Oh, do you have a question? You got a minute.
So about the storage, they're basically using the Merkle trees. Aren't the auditors basically the central authority? Because without the auditors in place, different clients could see different things.
Yeah, so they can be. What we did to ensure that this wasn't the case is that the actual contents of the map are just the hashes of the object. So when you're constructing the replica, it's actually several orders of magnitude smaller than the full data structure. So it's very lightweight to be an auditor. Anyone can download the auditing software, start it, and run them up. So we're assuming that there's going to be multiple auditors run by different people who are unlikely to collude.
Thanks.
Okay, thanks a lot.